So today, I'm going to explain quarks. Now, quarks are the fundamental building blocks of matter. Now, no doubt you've heard of atoms, and more likely than not, you've heard of the protons and neutrons, as well as electrons, that make up the atoms. Well, quarks make up protons and neutrons. Note, however, they do not make up electrons. Those are subatomic particles in their own right called leptons. But that's for a separate video. Now, there are 6 different types of quarks split amongst 3 generations. For the first generation, we have the up quark and the down quark. For the second generation, we have the charm quark and the strange quark. And for the third generation, we have the top quark and the bottom quark. Now, these last 2 generations of quarks are comparatively heavy and exceedingly rare. We are able to create them in particle accelerators, but when we do, they only last for a fraction of a second. This first generation, the up and down quark, is much more common. They're actually what makes up the protons and neutrons. Now, there are 4 properties for quarks which we can measure. There is mass, electric charge, spin, and color charge. Now, we're going to start with mass. Now, I'm sure you've all heard of mass. It's an inherent property of matter, it's responsible for gravitational forces, and it's usually measured in kilograms. However, for quantum particles, we measure it a bit differently. We measure it in mega electron volts per the speed of light squared. Now, an electron volt is a measure of energy. And in case you're curious as to why it can measure mass, remember this equation. So what we're doing is we're taking our energy, dividing it by the speed of light squared, and we're of course getting mass. Now, in case you're curious, 1 mega electron volt per the speed of light squared is equal to 1.783 times 10 to the negative 30th kilograms. So these are quite a bit less massive than these. Now, as to the mass of the 6 quarks, the up quark has a mass of 2.3 mega electron volts per the speed of light squared. The down quark is at 4.8. The charm quark is at 1,275, and the strange quark is at 95. The top quark has a mass of 173,000 mega electron volts per the speed of light squared, and the bottom quark is at 4,180. So as you can see, these 4 quarks have a comparatively large mass compared to the up and down quarks. Now, the quarks get their mass from the Higgs boson. They get it from the Higgs field. So whenever you hear about the Higgs boson, it is what gives quarks their mass. Now, the mass of a proton is 938 mega electron volts per the speed of light squared. And since a proton is made entirely of up and down quarks, you'll notice you'll need quite a few of these to make a proton. However, a proton only has 3 of these. So, the rest of the mass for the proton comes from the energy between gluons and quarks. So, all of our mass doesn't really come from the Higgs boson, it more just comes from energy as a result of the strong force. Now we have electric charge, which I'm sure you're also familiar with. It is the basis of electromagnetic forces, and is usually measured in a thing called coulombs. However, for quantum particles, we measure them in something called an elementary charge, abbreviated with this E. Now, an elementary charge is the electric charge of a proton or an electron. And 1 elementary charge is equal to 1.6 times 10 to the negative 19th coulombs. Now, as for the quarks, the top row of quarks, or the up, charm, and top quarks all have an electric charge of 2/3. As for the bottom row, or down, strange, and bottom quarks, they all have an electric charge of -1/3. Now we have spin. Now, spin is confusing. There is no analog in the macroscopic world to really explain it. The best way to think of it is as though the particle were actually spinning. And this is somewhat true because the particles do have some properties as though they were spinning. However, the particles aren't actually spinning. Nevertheless, all quarks, the up, down, charm, strange, top, and bottom quarks, all have a spin of 1/2. Now finally we have color charge. Now, color charge isn't actually a measure of color. Quarks don't really have color, they're far too small for that. Instead, it is more of just a way to describe the quarks. And like spin, there is no large-scale analog to color charge. Now, each of the 6 quarks can either be blue, red, or green. One quark is not a specific color. They can each be any of these 3. Now, when the quarks combine to form a subatomic particle, that subatomic particle has to have no color charge. It has to be colorless. And one way this can be done is by having a blue quark, a red quark, and a green quark together. The colors will combine and cancel each other out, and you will be left with a colorless particle. Now, this is what happens for protons and neutrons, and these particles are called hadrons. Hence, Large Hadron Collider, because it's colliding hadrons. Now, another way this could be done is by taking a quark, say a green quark, and combining it with an antiquark. Now, an antiquark will have an anti-color, in this case, magenta. Now, unfortunately, I don't have a magenta marker, so we'll just say that this is magenta. We'll pretend. Now, these two will combine, and they will cancel out, leaving this particle colorless. And this is called a meson. Now, I should have clarified more on antiquarks. Now, each quark has an antiquark, and the antiquarks all have the same mass and spin as their normal quarks. However, the difference is they have an opposite charge. So, the top row of antiquarks all have a charge of -2/3, while the bottom row of antiquarks all have a charge of +1/3. As well, instead of having the color charges, blue, red, and green, they have the color charges yellow, cyan, and magenta. But nevertheless, hope you enjoyed it, hope you learned something, and see ya!